Okay, folks. Section 4.5 is called a summary on curve sketching. So it's basically summarizing, putting together all the concepts that we've learned thus far, finding all these things associated with a graph. And then what we want to do once we find them all is build the graph, right? Draw it, sketch it. So that's the idea. So this is an interesting function, x times e to the x. And so in the book here, they give sort of a list of 8 guidelines. The 8th guideline is just sketch the curve once you've done all of these things, okay? So the homework associated with this chapter is going to say every problem says use the guidelines to decide which graph matches the function, all right? And most of these problems, they give you a function and then they're sort of multiple choice 4 graphs. So you've got 3 tries, you've got 4 graphs. So could you just guess your way through that homework? Probably. What's another way to sort of get the answers without going through derivatives and actually doing this process is you could use Desmos and or a calculator and graph the function they give you, look at the graph, look at your options, and figure them out that way, okay? So you can get the homework done that way, but that's not really the spirit of the homework. So there's a lot of functions. For some of those, if you feel like you've got the idea and you have it down and you know you could do the work if you had to, and you kind of want to take a shortcut, you know, I can't stop you. But I would encourage you guys, at least 1 or 2 of them to work through. Do this, and to me, I find it satisfying to not look at a graph at first. See what we can reason out based on all this information, build the graph, then look at Desmos, or then look in the book if there's an example. And to me, it's real satisfying if we can get it to look like it's supposed to, just naturally by all this analytics already. So I'm not going to number these things. I think they use letters actually, A, B, C, and so forth for these guidelines. But let's just sort of step through each one. If I run out of space, I'll start erasing some of this stuff. We'll do some derivative tests down here. But the first thing that the book suggests, if we want to graph the function, is to just ask yourself, what's the domain of the function, right? The graph, where's the graph going to exist? For what x values? Are there any places where it won't exist, like an asymptote or something? So here, x, I can plug any number in for that, and e to the x, his domain is all real numbers. So altogether, this domain is all real numbers, right? When in doubt, ask yourself, is there some sort of rule that might get broken here with this function? In other words, am I dividing, right? We can't divide by 0. Am I square rooting? Or do I have a log, right, where we can't plug in negatives? But I don't have any of that stuff right here. So e to the x is accepting, this is accepting, so all real numbers is our domain. Okay, moving on to intercepts. So the easiest thing to find, I always tell my pre-calc students, the easiest thing you can do in a pre-calc class is find the y-intercept of a function. And I guess it's the easiest thing we can do here. And to find the y-intercept, what we want to do is let x equal 0. Right? If x equals 0, then your coordinate is on the y-axis. That's your y-intercept. So simply f of 0 is 0 times e to the 0. E to the 0 is 1, but 0 times 1 gives us 0. All right. So I like to start with the y-intercept because this happens sometimes. The y-intercept is actually an x-intercept as well because y ended up becoming 0. So in other words, we found the origin is an intercept. Okay. So a function can only have one y-intercept if it has one at all. It can only have one. But a function can have more than one x-intercept. So to find x-intercepts, what we want to do is set y equal to 0, right? So just do the opposite. So standard procedure. What y, right? What's y? Well, y is the function values. So this could easily say y equals x e to the x. So in other words, set the function equal to 0, right? And then solve for any x's that make that true. So in other words, we want to do this. X e to the x is equal to 0. Set that and solve for x, all right? So that's a product. So just like when we factor quadratics and we get 2 terms equal 0, what we're doing then is we're taking advantage of something called the zero product rule, which says if you're taking the product of 2 quantities and the result is 0, then the only way that can happen is if one of these or both of these were 0, right? If they're both non-zero and you multiply them, you can't get a 0. So we can do the same thing here. We can apply the same reasoning. I've got a product that's equal 0, so that either means that x is 0, that would make that happen, or it means that maybe e to the x is 0, and if it was, then that product would also equal 0. So identifying x as 0, we already found that one because that was the origin, that was our y-intercept. So we've got that one already. This thing, there are no x's that make this true, right? So in other words, this equation has no solutions. So what that means is this graph only has one x-intercept, the one that we found. How do we know this has no solutions? So there's a few different ways you could think about this. You could talk about the range of e to the x. Range of e to the x is strictly positive numbers, so 0 to infinity, but not including 0. Right? And that comes from the graph of e to the x comes down like this, approaches 0 as x moves off to the left, but doesn't ever get there, right? Stays positive. So there's that. So you could argue that there's no solutions. Also, if you wanted to try to solve for x, how would you do it? You could use a natural log. You could use natural log of the left-hand side should be equal to natural log of the right-hand side. And what that does, natural log of e to the x unlocks the x. So we've got the x there, but natural log of 0 does not exist, right? 0 is not in the domain of our natural log, so I can't evaluate that, so this yields no solution, okay? So we found the one and only one intercept, this function f, and it is the origin. Alrighty. Why do we like intercepts? Because later we're going to, if we have mins and maxes or inflection points, those are going to be some key points that we definitely want to plot. They're going to really tell the story of the graph. But the intercepts are a few extra points that I like to say sort of like anchor the graph to the set of axes. It kind of ties it down to its spot, its little root. Okay. Moving right along, symmetry. So really just ask yourself, does this function have symmetry? And if so, how is that going to be useful? Well, if it is, if you know that it's got y-axis symmetry, which would mean you have an even function, then anything that happens on one side happens on the other, right? So you get sort of 2-for-1 function values. If you have a odd function, then that's got rotational symmetry around the origin, right? Like 1 over x or x cubed, and things like that are handy, again, because you kind of get freebies. So if you know what's happening on one side of the y-axis, then you sort of automatically know what's happening on the other side. So in general, it's good to consider, do I have some kind of symmetry? If so, can I take advantage of that? In this case, we do not have any kind of symmetry. In other words, this function is neither even nor odd. It doesn't have y-axis symmetry, and it doesn't have rotational symmetry. If we look at the pieces here, if I just look at the function y equals x, that is an odd function, right? That's this line, passes through the origin, and has rotational symmetry about the origin. If you rotate this 180 degrees, you end up with the same graph. So that's an odd function. If you multiply an odd function with an odd function, so kind of just step aside from this for a moment. If you do that, y equals x cubed is also an odd function, has this rotational symmetry, right? So odd times odd. If I ask you with real numbers, with integers, odd times odd, you tell me the result, 3 times 5, they're both odd, and the answer is odd, 15, right? So odd times odd for integers results in odd. For functions, it's actually a little bit different. They combine to form an even function, right? Because if you did x times x cubed, odd function times an odd function, you end up with x to the 4th. That has y-axis symmetry, right? That looks like kind of like a taller, skinnier parabola, x to the 4th. Now we've got y-axis symmetry. So this odd times odd became even, right? So the symmetry of graphs, the arithmetic of that symmetry doesn't work the same as with real numbers. But it's just something to think about. However, e to the x has no symmetry. E to the x is not symmetric. So I looked at a graph of that a second ago. E to the x is low to the axis here and then rising over here, right? So it behaves completely differently on one side of the axis from the other. So it doesn't have y-axis symmetry, and it doesn't exist down here, so it can't have rotational symmetry. So e to the x is asymmetric, and then you multiply that by the x, we lose our symmetry, okay? So no symmetry. While we're thinking about symmetry, though, for this function, let's just sort of think about the nature of the function. So without calculating function values, let me look at e to the x again. So I've drawn it. This is the third time. I talked about the range of it earlier. E to the x is always positive, right? It gets small here. It gets close to 0, but it's still positive. So e to the x is always positive, right? And then you're multiplying that by x. So we already know when x is 0, this function f is 0. So we'll pass through the origin. When x is positive, so as we move to the right, we're going to have positive times positive, so the function will be, so f will be positive. So f will exist in quadrant 1 to this side of the y-axis. When we move to this side of the y-axis, then x is negative, we're going to have negative values times e to the x will still be positive. So negative times positive is going to be negative values. That tells me that for negative x's, f is going to be below our x-axis, so down here in quadrant 3. Okay, so that's not quite really symmetry, but I kind of know a little bit now of where the graph is going to belong, and I know it's going to get from quadrant 1 to quadrant 3 by passing through the origin. So, worth noting. All right. Okay, asymptotes. So, well, I guess I can leave the question. Do we have any asymptotes? So there's 2 different types. I guess you could say 3 different types of asymptotes, but we really don't deal with slant asymptotes too much, or we haven't in this class yet. But vertical asymptotes, will arise if you've got a non-zero number over a zero number. So if some x value plugged into your function results in this, then you're going to get a vertical asymptote. All right. However, remember the domain of this function was all real numbers. We're not dividing by anything here, so we can't get this scenario. So we're not going to have any vertical asymptotes here. All right. What about horizontal asymptotes? So horizontal asymptotes, there could be one on either side. So these are limits at infinity. In pre-calc, we call this end behavior. What's the end? What's happening towards the ends of these graphs? So in other words, what's the limit as x approaches infinity, or the limit? So that means move to the right, or the limit as x approaches negative infinity, right? So go extreme to the left. What's happening to the function here, right? Is there any kind of behavior that we could, if this limit exists, then that's really telling us that as x moves on, if the limit exists as a real number, then as x gets really large, the function values are approaching some real number. That yields a horizontal asymptote. So the limit as x approaches infinity, positive infinity, of x e to the x, what's going to happen? As x approaches infinity, then x is approaching infinity. E to the x is also approaching infinity, right? In other words, getting large, you multiply them, so overall getting large. So I would say there's no asymptote going on to the right? This function is just going to keep growing and growing and growing, but not really leveling off to any kind of asymptote. What's happening with this? So this limit as x approaches negative infinity of x times e to the x, right? Let me draw e to the x again. This graph is coming in handy for this problem. E to the x looks something like that. As we move to the left, this is approaching 0, right? So e to the x is going to 0. But as x approaches negative infinity, x is approaching negative infinity, right? So when I try the limit, I get this expression, negative infinity times 0. So we got to be careful here. You might be saying, oh, wait, anything times 0 is 0, right? So this equals 0. Any number times 0 is 0. Infinity is not a number. And this 0, e to the x is never actually equal to 0. Right? E to the x never really equals 0, so we're not actually multiplying by 0 here. E to the x is some small positive number times a really, really, really big negative number. So the answer, if it's anything, is going to be something negative, but what's the result of taking something close to 0, so really, really small, and multiplying it by something really, really large, right? Who wins? Right? As x goes to negative infinity, this guy's getting small, so wants to shrink it to 0, but this guy's getting really, really large, approaching an infinite value. So who wins, right? Is it shrinking faster or is it growing faster? So believe it or not, this is actually an indeterminate form. It doesn't look like what we saw in the previous video from L'Hopital's, but it is an indeterminate form. And the reason is because I can rewrite this by moving one of these things maybe to the bottom, something like that, make a fraction out of it. You can kind of think in these terms. 0 and infinity are kind of like each other's reciprocals. Right? You can't really divide by 0. So 1 over 0 is not really equal to something. But if you find that from a limit, that means that a fixed number divided by something really small becomes really big. Right? So there's kind of that idea as limits are concerned. And same idea, if you've got a fixed number, let's say 1, and divided by something really, really large, then the result is really, really small. So again, you can't actually perform these divisions with numbers, but as limits are concerned, you can kind of think of 0 and infinity as each other's reciprocals. So that means if I can get like the reciprocal of the 0 down here or something like that, maybe then I can get an infinity over an infinity and try a L'Hopital. So let me set that up. I want to try this. The limit as x approaches negative infinity of x e to the x. So what I want to do is rearrange this so I can try to get a L'Hopital. Okay? X is going to, it's negative infinity, but I'm just saying it's an infinity. So x is sort of growing and growing and growing. Let me see what I can do with this. E to the x, I claim, is 1 over e to the x. That's one way of doing it. I'll probably state this in a different way. But in other words, the reciprocal of a reciprocal is itself. So the reciprocal of e to the x is e to the x. Okay, and then 1 over e to the x is e to the negative x. So if you want to go that route, you can. Actually, though, if you just want to play around with exponent rules, here I've got e to the x over 1, right? We can move this across the fraction bar by changing the sign of the exponent. So this is the same as that, right? So we should be able to do that, so that's fine. So what that means is I want to do this. the limit that I'm looking for is the same as this limit, x over e to the negative x. Right? So instead of multiplying by e to the x, I'm dividing by e to the negative x. Same exact thing though, just playing with exponent rules. What is that going to get us? So now e to the negative x, what does that graph look like? That is a mirror image reflection of e to the x. So that's this. So y equals e to the negative x is this graph right here. So now, as we let x go off to infinity, x is going off to negative infinity. I'm sorry, as x goes to negative infinity, the top's going to negative infinity. This graph, as we move to the left, right, as x goes to negative infinity, moving to the left, is also climbing now to positive infinity. All right, so we got negative infinity over positive infinity. Remember, negatives aside, positives and negatives, that's an indeterminate form. An infinite value over an infinite value, which means they're both growing, but we want to know which is growing faster. Okay? So we looked at the indeterminate forms like this in the previous video. 0 over 0, infinity over infinity. If you find that you get something like this, a product of 0 and infinity, or maybe vice versa, right? You can convert the expression into something that's going to yield one of these, which means these are sort of setting you up to use L'Hopital's. All right, so let's use L'Hopital's if we're set up to do it. So we got the indeterminate form. So that now we know we can use L'Hopital's. So this limit is equal to this limit that I'm going to write because of L'Hopital's. So I'll point to that equal sign. And so if I'm taking L'Hopital's, I'm taking the derivative of the top. So derivative of x with respect to x is a 1. The derivative of e to the negative x, I've just got a mini chain rule. That's e to the u, so it reproduces an e to the u, times the derivative of the u, or the derivative of that exponent. Derivative of negative x is negative 1, so I end up getting a multiplier of negative 1, which I can just put up front right there as a negative. Okay, so there we go. So we got the, now we're going to take this limit. Notice, whatever happens in the denominator, I have a 1, a fixed integer up top, which means I'm not going to get an indeterminate form. So that means this L'Hopital application worked. Now, what does this graph look like? So let's think about our reflections. Regular e to the x we looked at, the negative exponent reflected it like that across our y-axis. Then we're negating it, we're multiplying it by a negative 1, which flips it down here. Okay, so negative e to the negative x is this graph down here. And as x approaches negative infinity, this graph is going towards negative infinity. All right. So I try, kind of like direct substitution of just using the graph. As this graph, negative e to the negative x, moves to the left, it's plunging down towards an infinite value. The fact that it's negative doesn't really concern me. I've got a fixed number that's being divided by larger and larger and larger items, and so the result of that limit is going to a 0. Alrighty, so that's what we've got right there. Which means, and as we approach, so the values are, as x approaches negative infinity and we plug in particular x values, they're negative. So we have positive over negative. So this limit, this function is going to be approaching 0, but the function values are going to be negative, right? And as we approach negative infinity, as we come up this way, remember that we expected our graph to live in quadrant 3. And so that kind of makes sense that we're going to be coming up towards the x-axis as we move to the left. All right, so moving right along, we've got a lot going on here, only kind of halfway through our little checklist here, which is why you might want to take the shortcut for some of the homework problems. But again, we're explaining this all thoroughly. Horizontal asymptote, I could write this two different ways. I could write it using the limit notation. That might be helpful. Limit as x approaches negative infinity of this function f is 0. Right? Why do I want to write it like that? Well, that tells me that the horizontal asymptote is the line y equals 0. Okay, so that's a line. However, the graph is only going to hug this asymptote or approach the asymptote to the left, right, as x approaches negative infinity. We claimed as x approaches positive infinity, the graph was just increasing, right? It was just going to go up itself. And so this is what we might call a one-sided asymptote. It's only going to work or only going to get close to the function on one side of it. Okay, so here we go. Other than using derivatives to use L'Hopital's rule, other than that, everything we've done so far really hasn't been too much calculus. but now we're going to do this, right? Now we want to do our first and second derivative tests to find mins, maxes, and inflection points, basically. That's what all this says. Whether or not you use your first derivative test or your second derivative test, remember the first derivative test relies on increasing and decreasing. The second derivative test, you can kind of forego that, perhaps, and figure out your mins and maxes based on your second derivative. However, to complete these guidelines, regardless of how we identify mins and maxes, we still want to know where the function's increasing and decreasing. So let's do that next. So now we're going to start taking derivatives. So the derivative of f prime, we have a product here, so we've got to use the product rule. And we've actually done this one before. I think the video where we introduced the product rule, I did this and I took several derivatives. This looks a little bit familiar. I think there was a bonus extra credit that nobody emailed me about, asking what like the 25th derivative would be or something like that. However, let's say the first function, x, times the derivative of the second, derivative of e to the x is e to the x, plus the second function, e to the x, times the derivative of the first function, which is a 1. So we end up with just plus e to the x. Okay, that's our derivative. Domain of the derivative still also all real numbers. So if we want to find critical numbers now, we are looking for set f prime equal to 0 to identify critical numbers, which are potential mins and maxes. All right, so that means, let me just do it up here. Set that equal to 0. So I want to see what I can do with that. What I don't want to do is start subtracting stuff over and trying to divide by e to the x, because, well, e to the x is never 0, so you might try that. I want to try to factor and use my two factors equaling 0. So here we have a common e to the x, so let's factor that out, and then I have x plus 1 times e to the x is equal to 0. This is a better route for trying to find where this is equal to 0. One method sometimes is subtract things over, divide things. When you do that, though, you have to be careful of dividing out something that gives you a 0, which happens sometimes. Here, I think with e to the x would be safe. But let's just do it this way. What we said earlier now, I've got a product that equals 0. All right, and so this product can only equal 0 if this term equals 0 or if this term equals 0. Right? We've already looked at this. No solutions to that. So this doesn't yield any solutions. This, if x plus 1 is equal to 0, then that means x is negative 1. So if when x is negative 1, the derivative is 0, which means the graph is flat, I like to say. So that's a potential min or max right there. All right. Okay. That's the only one. So that's the only critical number that we found. So let me just make a little note here. F prime critical number, and x equals negative 1. So I'll probably come back and use my second derivative test just to show how it works. But let me do the first derivative test now, which is going to test for increasing and decreasing, and therefore perhaps locate a minimum or maximum. So first derivative test for locating mins and maxes says set up your number line, label it with the derivative you're going to use, put the critical numbers there. So we only have one of them here. And then I've got to see what's going on either side here. Okay? So I can choose any number to evaluate into the derivative here. If you can use 0, that's probably easy. I mentioned earlier, remember about finding y-intercepts, you said was easy, because you're evaluating something at 0. So here, if I take f prime of 0, what are we going to get? 0 times e to the 0 is 1. So 0 times 1 plus e to the 0 is 1. Let me erase the equal 0. That was just to find our critical numbers. So we get 0 plus 1 is 1, right? And that's positive. So that's all we really care about. So the derivative is positive here. So f prime is positive, which means f is increasing. And so I can draw the little arrow there to indicate that. And let's see what happens on this other side of negative 1. So let's say f prime of... So someone in class asked if I have to do something, the next integer, or if I can do something really large. Here, anything you choose is really not helpful because I've got this funky base. Remember the factored form might be helpful. So let me say negative 2. Right, I'll choose the next integer. So what I'm going to get then, if I use the factored form of the derivative, we're going to get negative 2 plus 1 times e to the negative 2. Well, e is always positive. Even to negative exponents, that is a positive function. Negative 2 plus 1 is negative 1. So if you've got a negative times a positive equals negative. All right, so f prime is negative. Oftentimes, I do like the factored version, okay? If you try it the other way, then you're plugging into this thing. You've got negative 2 times e to the negative 2 plus e to the negative 2. You see the problem with that, though? I mean, you could probably reason out what's going on here, but e to the negative 2, what is that equal to? Right, some decimal, not exactly sure what's going on there. So the factored version is nice because then you've got the product of terms, and you can reason out product of positive times negative. We know what that is. Here, if you're adding a positive and a negative, the result could vary. Okay, so f prime is negative, function's decreasing. We found a minimum, right? We found a minimum right there. So we did accomplish basically these two steps simultaneously, right? You find minimums and maximums by considering the increasing or decreasing nature of the function. If we were on campus and I was collecting this as a full assignment, I would ask, where's it increasing and decreasing in integral notation, right? So actually tell me that. So here f is decreasing. Decreasing for all these values, everything to the left of negative 1. So on negative infinity to negative 1. Increasing and decreasing are always over open intervals, so we use round brackets. And f is increasing on the interval from negative 1 out to infinity. Cool. So we stated that clearly now. All right. And we found a minimum. So min is negative 1, comma, we've got to figure out what the function value is there, and max is, let's just write no max. All right, so this function did not have a max. We only had one critical number, and it turned out to be a minimum. F of negative 1 is, what are we going to get? We're going to have negative 1 times e to the negative 1. Well, what is that? E to the negative 1, let's do what we did earlier. Let's put that down to the bottom. So that's negative 1 over e. All right, and you can use a calculator. We'll do it later to approximate what that's equal to. It's something between, it's less, well, we've got a negative thing, but 1 over e is between 0 and 1, right? Because we're dividing by something larger than 1, but then we're negative here. Okay, so we got that negative 1 comma negative 1 over e is our minimum for whatever that's worth. Okay, let's go on, find the second derivative, look for possible inflection points, and then use the second derivative to determine that. And then we'll also look back to the, see if we can identify that minimum or maximum using the second derivative test. So, f double prime of x. When we did, you could use the product rule right now on that. When we did this in the video, we noticed that the derivative of x e to the x produced a copy of itself and an additional e to the x, right? So now as I take the derivative of this thing, which is the sum, I just go term by term. So the derivative of x e to the x produces x e to the x plus another copy of e to the x, right? So these two terms are the derivative of this, result of a product rule, plus the derivative of this e to the x is itself, right? So that reproduces itself as its derivative, and so we end up with that, right? So the further you take these derivatives, they kind of replicate extra copies of these e to the x's now. What am I looking at here? Now I've got x e to the x, so kind of the original function, plus 2 copies of e to the x. So I can call this x e to the x plus 2 e to the x. All right. The little extra credit hidden gem that I included in an older video is then we took the third derivative, which we're not going to use here for the graph. But the third derivative, this guy produces x e to the x plus an additional e to the x. Derivative of this is itself, and this now forms 3 e to the x. Right, so the third derivative was 3 e to the x. Fourth derivative would be 4 e to the x. So then I asked what was the, I don't know, 25th derivative, something like that. Okay, let's look for critical numbers of our second derivative. Let's see if we have any potential inflection points. So set that equal to 0, all right? And what can we do now? Let's do the same thing we did earlier. Let's factor. So I can factor out the e to the x. So I have x plus 2 times e to the x. to identify these critical numbers now. Same business as before, no solutions, and this, though, if this is equal to 0 when x equals -2, then there we go. So for f double prime, critical number, now we're looking at when x is -2. Okay? F prime, critical number, was x equals -1. So I'm going to keep that in mind. Okay, let's set up our number line and look at our second derivative. This video, I had a feeling, would be long, going on half an hour now, but there's a lot to do. Okay, double prime, let's label what we're going to do here. The critical number we just found was -2, right? Which means this is a potential inflection. Potential inflection point, IP. Okay, so what that means is I need to choose an x value from each interval, test it in the second derivative, use that to decide what the concavity is. If the concavity of the function changes at this point, then it's an inflection point. Otherwise, it's not. So I need to check something to the right of -2. I can check anything I want. Suppose I didn't do this earlier. Suppose we didn't do the first derivative test, right, where we set up that number line and looked for increasing, decreasing. Suppose we didn't do that. Let me take this critical number from our first derivative and use that as a test value for my second derivative. Okay, so I'm going to use that. That's going to do two things for me at once. It's going to do two things simultaneously. So let's do it. So that's that little arrow is showing my intention. But let's do this. F double prime of -1. All right. And so f double prime, the factored version, again, is going to be helpful. The factored version said this, x plus 2 times e to the x. And why is that helpful? Because I'm really just looking for positive versus negative. So f of -1 is going to give me -1 plus 2, which is going to give me overall a positive 1, times e to the -1. Well, 1 is positive, e to the -1 is positive, positive times positive is positive. So f double prime is positive here. Okay? That tells me two things. As far as concavity is concerned, remember, if you're positive, you're in a positive mood, your mouth is like this, you're smiling, and so we are concave up right here. So that's what the second derivative tells me about the original function, that f is concave up. However, the critical number from our first derivative, x equals -1, that arose from the fact that -1 made our derivative equal 0, which means the original graph is flat when x is -1. So we know the graph is flat. We also know at the point where it's flat, it's concave up. Therefore, that represents a minimum. Okay? So that, what I just stated right there, using the fact that the first derivative of this is 0, meaning the graph is flat, the second derivative is positive, meaning I'm concave up, you put those two facts together, guarantees a minimum right there. That is an example of the second derivative test for finding mins and maxes, right? So we could have avoided the whole increasing, decreasing business if we wanted to. However, I was looking for these interval notations, or these intervals rather. I wanted to know where it's increasing and decreasing. So I want to know everything myself, but we verified in two different ways now that we've got a minimum here. So good to know. Okay, let's finish up the second derivative looking for inflection points. So let's choose something to the left of -2. Let's say negative anything. Let's say -5. Okay, so what are we going to get there? Now I've got -5 plus 2, which is going to give me a -3 right there, times e to -5. So e to the -5 is positive, times -3 overall gives me negative. So f double prime is negative, which means if you're in a negative mood, you're frowning, so the function is concave down on this interval. Now, it was concave down, then on this side it's concave up, which means it switched concavity, which means we got an inflection point. Okay, so the inflection point is the point -2, comma, f of -2, right? That's always how it works. The function, you always use your original function to find y coordinates. So f of -2 is going to be -2 times e raised to the -2. I can move that to the bottom. So call it -2 over e squared. Okay. And 34.5 minutes later, we've done all 7 steps. So we looked at the domain, intercepts, we considered symmetry, we found an asymptote, we looked at where the function's increasing, decreasing, we found its minimum, looked for a max, and here we explored its concavity and found an inflection point. All 7 things. The last thing on the guidelines is sketch the function. Right now, this is what we've got. We've got everything in place. Now we can build the function. So to do that, I can get rid of this test, buy myself some space, get rid of this. I've got all my conclusions written over here. I will keep the increasing, decreasing up there, I guess, just for the fun of it. Cool. So I have my calculator handy, which I will use to estimate some of these values. Let's see what we've got here. The minimum is the point -1, comma, approximately, let's see, 1 divided by, where's my E? 1 divided by E is approximately 0.37. All right, approximately. I don't have notation to write that that's approximate, but that's okay. And that, well, that's negative also. So negative 0.37. 2 over E squared. So 2 divided by E squared is approximately 0.27, and also that's negative. So we've got -2, comma, negative 0.27. Okay, just estimates, so we can kind of plot this. The minimum, the y-coordinate is less than the that coordinate, which is good news, right? If that's the minimum, that should be the smallest y-coordinate that we have all around. Okay, so now that we see that, let's get our graph. So everything's kind of happening around the origin here. We've got the origin, we've got these points. So let me set this up. So I want to come back at least -1, -2. Let me calculate. Do I want to do that? Nah. Let me plot what we've got. Let's say down here is -1. All right. So I'm going to kind of ballpark these things the best I can. The intercept 0, 0. Not a max, not a min, not an inflection point, but nice little point that we can plot there. -1, and let's just say about a third in the negative direction. So maybe around somewhere around there. Put a nice big dot. So let's say that's our minimum. This guy, -2, let's say that's about a quarter, right? So if I had a half, and then half of that is maybe around there. So -2, maybe I'm around here. Okay. What else do we need? I've got the inflection point, I've got a minimum, I've got this intercept, and then what else could I really plot? I know the horizontal asymptote is the line y = 0, so sometimes I draw that as a dotted line. Remember, for negative x's, this function is always going to be in quadrant 3, we argued, right? So this was its minimum, and so here, what's happening is it's just, as we move this way, it's just getting closer and closer and closer to that x-axis. So it's going to stay in quadrant 3, but build up, approach that value of 0. That was reflected as our horizontal asymptote over there. I erased the concavity test, but when we found that this thing was an inflection point, remember this point to the right of this, we were concave up, which jived with the fact that we had a minimum right there. And this was concave down. Right? So I want to do my best now when I graph this thing to try to show that concavity and maybe try to show the switch here. What's going to happen as I move to the right? Well, this thing is just going to start growing, and it's going to grow pretty quickly. F of 1 is 1 times e to the 1. So that's e, which is approximately 2.7. Right? So that means if this was 1, then 2.7, you can't see it, right? It's way up on my wall up there near the ceiling. So that's when x is 1. This guy is way up, off the board. When x is 2, now I've got 2 times e squared. E squared, I think, is around 7 times 2, 14. It's going quick, right? We knew that the limit as x approaches infinity from the right was infinity. It's going to go up. But it's going to go up pretty quick. So there's not really a whole lot I can graph over there. So that's it. This resulting graph might seem anticlimactic. This is our minimum. The graph, the slope, the derivative right there, the first derivative was 0, which means the graph is flat there. remember, it's not flat for like an inch or for any length like I'm drawing it here, but I'm just trying to emphasize, I'm basically drawing the tangent line first and then using that to sort of keep it flat there so I don't end up with looking like something like too pointy. Right? I want it to look nice and smooth transition. And this whole piece should be concave up. That's what we determined. So we want to kind of draw sort of a cup-shaped thing through this little flat bottom and then skyrocket up there. Cool. That piece is concave up. This portion was concave down and is all going to live beneath this axis. So concave down, something like that, and get closer and closer, and that's it. And can we see the concavity? Can we look at tangent lines there? Here, the tangent lines live below the curve, all the way over here, below the curve. At that inflection point, it should pass through, and then here and here switched up there. Alrighty. So, after all that, I mean, does this function look that cool? No, there are cooler looking functions that have different asymptotes and, you know, all loop-to-loops and stuff like that. But, had a lot going on, a little bit of everything, all right, except symmetry. Okay, so that'll do it for this example. There's your list of guidelines. So the guidelines are all listed on pages 315, the beginning of them, and then on 316, so you might want to jot them down. That's the way to graph a function. Alrighty, there you go.